Hello, this is my first lab report for Physics 2211. The purpose of this lab is to analyze the motion of an object with respect to Newton's second law, which states that velocity final is equal to velocity initial plus net force divided by mass multiplied by the change in time. The object in this experiment is meant to have a zero net force, which means that it should move with a constant velocity. With a constant velocity, the final position can be calculated by the initial position plus velocity times the change in time. Here I conducted motion analysis of an object with constant velocity using tracker. My start frame was 39, which is where the object seemed to stop accelerating and reach a constant velocity. My end frame was 100, which is right before the object seemed to slow down, giving me a total of 61 frames. The frame rate was 29.98 frames per second. The change in the time between frames was 0.033 seconds. I inserted a calibration stick of 0.073 meters for the diameter of the object to allow tracker to accurately measure the distance. I inserted a coordinate system so that the movement was in the negative x direction starting at the origin. I inserted mass points at each frame to track the motion of the object. The mass points may have been off-center, which we will see later on. I then created a computational model using the starter code provided with a few adjustments. I changed the mass to be 0.374 kilograms, adjusted the starting velocity to be negative 0.465 meters per second in the x direction, which was estimated using the first two data points on tracker and the change in position over the change in time. I adjusted the starting position to be at 0.01918 as it was in frame 39 on tracker. I made delta t equal to 0.033 seconds to match the frame rate of my tracker video. Although the instructions said that delta t did not need to be equal to the frame dt, I found it easier to graph and compare the data when they were the same. I made Newton's second law loop while t was less than 1.935 seconds so that it would continuously loop until the time from frame 100. I set the net force equal to 0 because we are assuming friction to be negligible. I inserted Newton's second law as ball velocity equals ball velocity plus net force divided by ball mass times delta t. I edited the line that calculates the ball's position to be ball position equals ball position plus ball velocity times delta t. Here we see the motion model and the velocity versus time graph, which is perfectly constant. The program also produced a position versus time graph, which I didn't include here because it's on the following slide. Here we have a comparison of the observed motion and the predicted motion. As you can see, there is a bit of variation. I believe the blue line jumps up and down a bit because I may not have selected the exact center of the object when using tracker. The two lines become further apart because the computational model does not account for deceleration due to friction between the object and the floor. Some assumptions that were made in this experiment are that friction is negligible, net force is 0, and velocity is constant. In the experiment, the velocity was in the negative x direction, but if the axis were flipped, the velocity would become positive, but the magnitude would remain the same. We know that gravity, the normal force, and the force pushing the bottle across the floor are all acting on the object, but we did not account for friction or the floor being uneven. We know the floor was a bit uneven because when I placed the bottle on the floor without pushing, it rolled across the room. We cannot tell exactly how many forces are present, but we know that the net force is pretty much 0 because of the almost perfectly constant velocity. In conclusion, we were able to see Newton's second law in action and verified that a net force of 0 will result in a constant velocity. We can see this in the equation for Newton's second law here. When F net is 0, the equation becomes V final equals V initial. We were able to prove this with our experiment, as shown by the constant slope of position versus time when the slope is the velocity. However, one comparison to note from this lab is that the observed position did vary a bit from the computational model. This variation was caused by user error with the center of mass on tracker as well as the model not accounting for friction. Some possible ways to improve upon this lab would be to have a higher quality camera to gain more precise data by decreasing delta t, or marking the center of mass to make tracking more accurate.